Oftentimes, when people speak of hit and miss engines, they're described as the engine hits, the flywheels get to going too fast, and the engine then coasts until the flywheels slow down enough that it needs another hit. I think there's a more interesting way to look at how these engines operate. This one happens to be a 2 horsepower, and I'm going to say that it's rated at 600 RPM. So what does that mean? Well, first of all, it's 2 horsepower. What is a horsepower? A horsepower is 550 foot-pounds per second. That means if you have 1 horsepower, you should be able to lift 550 pounds 1 foot in 1 second. So if you had 2 horsepower, you should be able to lift 1,100 pounds 1 foot in 1 second, or any combination thereof. If you're 2 horsepower, you ought to be able to lift 1 pound 1,100 feet in 1 second. As an analogy, I remember in junior high, we had a stairwell that was about 10 feet vertical height. In other words, from the bottom, if you look straight up, it would be about 10 feet up there. We would run up those stairwell. If we weighed 160 pounds, when we got to the top, the energy would have been 1,600 foot-pounds. That is 160 pounds times 10 feet of vertical rise, 1,600 foot-pounds. If we did that in 3 seconds, that means that we were developing a little more than 500 foot-pounds per second. So we generate about a horsepower running up those stairs. So let's take this engine, 2 horsepower, 600 RPM, and let's assume it's under a full load. If it is, then it will have about 300 hits per minute or 5 hits per second. 2 horsepower, it's 1,100 foot-pounds. So at 5 hits per second, each hit then is about 220 foot-pounds. All right. So every hit we get 220 foot-pounds of energy delivered to the flywheels. The flywheels distribute that over time. Now let's unload this engine. Just take all the load off, and let's say it's only hitting maybe 30 times per minute. At 30 times per minute, that's about a half a hit per second. Each hit, remember, is 220 foot-pounds. So we now are doing about 110 foot-pounds per second. That happens to be almost exactly 1/5 of a horsepower. So rather than thinking of the flyball governor as letting the engine get a little going too fast and then slowing down, think of it, the function of the flyball generator as regulating power. So when this thing is idle back, so to speak, hitting only maybe 30 times per minute, this thing is operating as a 1/5 horsepower engine. The fuel consumption is about the same as a 1/5 horsepower engine, and the heat generated, the water hopper is going to get hot just like a 1/5 horsepower engine. So I think of thinking of the flyball governor as regulating power as a nice way to look at a hit-and-miss engine. We've said that the purpose of the flyball governor is to regulate the power out of these engines. When the engine needs to deliver very small amounts of power, they don't hit very often. And when we get to full load, they will hit every time. So I wanted to demonstrate that. I wanted to put varying loads on one or more of these engines and just listen to how many times it hits. As we get up to a full rated load, it ought to be barking every time it needs to. I also thought, okay, as I vary the loads, if I could measure how much load I had on it, I could correlate then the sound of the engine or the hits and the misses versus load. So that's the purpose of this activity. So the question becomes, what am I going to use to load this engine, hit and miss engine, so that I can hear the difference in sound, or that it hits more often as I load it? I want something that's not too big, not too messy, maybe something that the output is something that's useful, and I want to be able to measure in some manner how much power is being needed to turn this load. At a lot of the shows, we see corn shellers and grain grinders, etc. Grain grinder, if I run it for 2 or 3 minutes, I might be able to hear the difference. The problem is the grain grinder, for example, is quite noisy. You can barely hear the engine over its noise. I have to feed a lot of corn into it, and I get a product out, ground corn, that I don't know what I'm going to do with. So a lot of those kinds of loads don't seem very reasonable. I'm standing here looking, and maybe you can see it. I have a 1945 Ford pickup truck. See if I can get it around here far enough. That I redid, and I put disc brakes on the front. So maybe I could take the old brakes and somehow put a pulley on the system, and as I applied pressure to the brakes, it would take more to turn. The problem with that is I don't know how to measure the power required at some pressure level on the brakes. So I got to thinking, when I built that truck, I also put a 100 amp alternator on it. Let's call it a generator for a minute. A 100 amp alternator at 14 volts is 1400 watts. And as you may know, 745 watts is a horsepower. So the alternator on this old 1945 truck, the alternator that's in it now, at 1400 watts, takes about 2 horsepower to turn if it was 100% efficient. It's probably not 100% efficient, so it maybe takes 2.5 horsepower to turn that alternator. The output is not so nasty. In fact, headlights, both the lower and the low and high beams, are about 45 watts. So if you hook them up in series, it's about 90 watts per bulb. So 15 bulbs, I'd be able to load that alternator and know that it would take more than a couple hundred horsepower to turn it, or a couple of horsepower to turn it, and I can measure it. I can measure the current, I can measure the voltage coming out, so it's quantitative. So that sounds like a pretty good idea. The alternator's not too big, and so I'm going to start there. Okay, before we get too deep into this, let's do a little experiment here to demonstrate how the generator is going to work. Here I have the core of a DC motor that used to run my mill and lathe. The rotating assembly burnt up, and I pulled it out and chucked it. So what's left here is just the outer core of that motor, but it has 2 very strong permanent magnets in it. You can see that I stick a pocket knife in here, and hard to get it out of there, actually. I used a compass and found out that this happens to be the North Pole, and this happens to be the South Pole over here on this side. Now, the interesting thing is to put a wire in that magnetic field. Here I've stuck a wire in, but that won't give me much of a result. So let me instead stick 60 wires in. I've got this 2x2, and I'm having a little trouble because the end of the 2x2 has got a steel lag bolt in it, so I can push it through the bearing hole. Okay, I've got it in there now, and there's 30 turns on here, so I got 30 wires going by the North Pole. I got 30 wires coming back by the South Pole, and I've connected those then to this amp meter. And actually, it's a microamp meter because I'm not going to get much here. But if you notice, if I turn this, I get current. So if I move this wire in a magnetic field, I get current. And in fact, this 60 wires and turning it quite slowly, I get about 10 microamps. So if I were to maybe have several hundred turns here, and then I had maybe 50 different groups of these coils around this thing, and I were to turn this thing at a couple thousand RPM, I would actually get probably 100 amps out of it. But so that's the concept of the generator. But let's try something a little different. We have shown that if we have a magnetic field and a wire and we move the wire, we get current. What if we take the wire in the magnetic field, and here I've hooked a small 6-volt battery up. What if we actually push current in? Look at that. This thing moves. So I'll turn the polarity around a little bit and you can see it. If I have a wire in a magnetic field and I put current in the wire, I get motion. In essence, a DC motor and a DC generator are one and the same thing. If I take a DC motor and I turn it, I'll get current out. If I take a DC generator and I put current in it, I will get a motor. And that'll be kind of important here when I get to the final assembly. Now here's kind of an important aspect of this thing. We have it hooked up as a generator. As we rotate the wires in the magnetic field, the current in those wires creates their own field, and that field interacts with the magnetic field of the magnets in a negative manner. So it becomes more difficult to turn. So as I take more and more current out, or I put a heavier load on the output of this generator I've built here, it will become more difficult to turn. And in fact, if let's say I'm getting maybe 70 volts out, and I take 10 amps at 70 volts, that's 700 watts. That's close to a horsepower. Remember, a horsepower is 745 watts. So it would take a horsepower to turn this assembly inside this magnetic field if I was running it at 70 volts and 10 amps. So by measuring the output current and voltage as we turn this thing, we'll have some idea of how much power the hit and miss engine is having to put into this thing. So if I have a 1.5 horsepower hit and miss engine, if I load it up with 1.5 horsepower, about 1,000 watts out of a generator, then I should have it loaded about 100%. So it's measurable at least. As it turns out, a lot of these big health clubs have, of course, many treadmills. And routinely, after a treadmill gets so many hours on it, they will come in and replace the electric motor that's driving that treadmill. And if you're lucky, you can probably pick one of these things up free from the service company. This happens to be a treadmill motor. It's rated at 220 volts DC. So they take a 200 volt line, rectify it, get 220 volts DC. 3,400 RPM, it's rated at 3.2 horsepower. So in our earlier discussion there, we said a motor's a generator and a generator's a motor. So I ought to be able to take this treadmill motor, and if I spin it, I ought to have a generator out of it. So you can see I've hooked it up to my little meter that we had before. And if I barely turn this assembly here, I peg my meter. If I go the other way, of course, it immediately pegs in the other direction. So this looks like a real opportunity to load up one of these hit and miss engines. This is a big flywheel that smooths the motion out on a treadmill as your feet slap down. Big old heavy flywheel. Looks to me like it's a flat belt pulley. So it looks like I could put a flat belt on this and drive this thing. And if I got up around 3,400 RPM, I'd be getting a lot of voltage, and it'd take 3.5, 4 horsepower to turn it. I don't want to do that. I want to turn it slower. I want about 70 volts out of it or so. And being 70 volts DC, that's fairly safe, and I don't have to worry about it. So that's kind of the plan here, is to take one of these old treadmill motors, use this big flywheel as the pulley, take the output, spin it at a rate that will give me about 70 volts, which is probably a couple thousand RPMs, 1,500 to 2,000 RPMs, and light up some regular 120 volt light bulbs. They'll light up pretty nicely at 70 volts or 60 volts, even 50 volts probably. If they're 300 watt bulbs, they certainly won't be consuming 300 watts at 60 volts, let's say. But I can measure the current and the voltage coming out of this beast, and I'll know exactly how many horsepower it's taking to turn it. So here's the final assembly. It turns out I'm a John Deere collector, so it's sitting on a set of John Deere trucks. But you can see here what we discussed, the treadmill motor, which is going to be used as a generator. I'm using a narrow, actually, but very tight flat belt on the flywheel. That's being driven off of a jack shaft. I've got a jack shaft here that's left over from the earlier light plant work, but I have to get the RPMs up. We thought about 1,500 to 2,000 RPM. So it turns out that this pulley over there is slightly larger than the flywheel on the motor, so I do get a little improvement in RPMs there. The load, you can see down here, I happen to have an old antique voltmeter and an old antique amp meter. The amp meter goes 0 to 10 amps, the voltmeter goes 0 to 150 volts DC. You can see a switch there. That switch will turn on these first two bulbs. They happen to be 300 watt bulbs. But again, as I said, at 50, 60, 70 volts, they won't consume that. There's a secondary switch right there, right there, that will turn on the last 3 bulbs. I know that the two on the left are 300 watts also. The one smaller one is 200 watt bulb. And what I found with a 1.5 horsepower engine, that's about right. I can change those bulbs. I can put another Y connector for bulbs in there and put more bulbs on, but that seems to be working fine. I need a little weight on the front end, so I got a concrete block painted John Deere green to hold the front end down, because when you tighten up the belt so tight, things start to move around. And you'll see over here, I've got a bar that goes over to the wall that keeps the back end from sliding to the left. To keep the belt tight, down underneath there is another bar. It's one of those bars that goes across the back of a pickup truck, so your stuff doesn't fly out. In order to get the RPMs, we said these hit and miss engines like to run 500 or 600 RPM I need a big pulley here on the front end and a very small pulley down there. I made that pulley out of aluminum. That's about 4-inch pulley, and it's crowned to keep the belt on. And I made this 12-inch pulley out of a piece of 12-inch pipe and some other stuff, so that I can get a 3-to-1 improvement in RPMs there, and I get a little bit improvement in RPMs on those two pulleys over there. The engine I chose to use is an antique John Deere. It's a very early John Deere spark plug or battery powered. It's unrestored. You can see John's original paint there in yellow, and John's original green paint there on the water hopper, and even down on the wood skids there's still some green paint down there. So that's what we're going to turn this system with. It's